Good Monday morning, witches, wizards, warlocks, muggles, and squibs. Hope you guys had a nice weekend. It's beautiful weather. If you had a chance to get outside and go for some walks and get a little fresh air and recharge your batteries, that's best thing you can do in this lovely springtime weather. So, hope you're all well. I'm going to apologize now because today's lesson is a big one. It is probably, well, I know it's the largest one in the whole chapter. So, unfortunately, it's going to take a little bit of while to get through. There's a lot of information today that sets you up for the rest of the chapter. Plus, we've got the Harry Potter stuff going on. So I'm keeping you guys off the streets and out of trouble today. Okay, here we go. So today's topic is all about looking at any compound and then deciding what does this thing look like in water. So the vocabulary that we use is major entities present. Entities are parts. So what are the major parts present when you put these things into water? And we're going to have lots of vocabulary today as you guys learn all the terms for the different kinds of solutions that you'll see in Chem 20. So I'm going to go through some of these examples using the vocabulary and the skills. And then after these examples, we'll go and look at the skills and the vocabulary step by step. Sound good? Okay, so sodium chloride. So I know that sodium chloride is an ionic compound. So its formula is NaCl. And if I go look on my solubility chart, sodium chloride, there's the Cl minus, and the Na plus would be in the most category because it's none of those. So it has high solubility. So NaCl aqueous, drop it into water, and we get Na plus aqueous and Cl minus. And the vocabulary with that is it dissociates into its ions. Calcium hydroxide, CaOH2, aqueous in water, and hydroxide is right there, and calcium is right there. So remember this cutoff, this is the high or very soluble. So it's high solubility as well. So same thing. It breaks apart into its ions, Ca2 plus and 2OH minus aqueous. So that's what it would look like in water. Calcium ions, aqueous, and hydroxide ions. Okay, calcium carbonate. So calcium carbonate, if I go look it up, there's carbonate. Calcium is not one of those four. It's down here. So it's in the slightly soluble or low solubility. So because it's low solubility, it won't dissociate into its ions. Most of it stays together as a solid. Remember, ionic compounds are solids, even in water, unless they have high solubility. Okay, moving on. Hydrochloric acid. Now, hydrochloric acid is a strong acid, Sa. I know that, and I'm going to give you the chart for that in a minute. So strong acids ionize. What does ionize mean? It kind of looks like dissociate. It's a molecular compound, but it breaks apart into an H plus and a Cl minus. Now, acetic acid is guess what the W stands for? Weak acid. So weak acids, this is the formula for acetic acid, CH3COOH. Weak acids dissolve aqueous, but they don't ionize, or only a small amount. So this is the major form present, whereas for a strong acid, this is the major entities present. So most of the acetic acid stays together as one molecule. Most of the hydrochloric acid ionizes into its two ions. Copper is easy. It's an element, and all elements just keep their state. Copper is a solid, so in water, copper is a solid. If you don't believe me, go find a penny, put it in a glass of water, and see what happens. Surprise, surprise. Okay, moving on. Sucrose. Okay, sucrose is a molecular compound. Here's the formula, C12H22O11. And I know that it is polar, and because it's polar, it will dissolve. So it is aqueous in water. It dissolves, but does not break apart into ions. There are no ions present, so it dissolves. Gasoline. Now I know gasoline is non-polar. and its formula is C8H18, and it is a liquid. And when you put it into water, it just floats on top as a liquid. So that's what it looks like. It does not dissolve, does not dissociate, and it does not ionize. It's a lot of vocabulary. Don't worry, we're going to go through all this stuff step by step. Amortensia, for those of you that are Harry Potter fans, amortensia is classified as bewitched. Not easily made. And you could talk to, who's the master of potions? Snape's pretty good. Who's the other guy? His name escapes me. The one that took over in like book 4. Slughorn. Yeah, Slughorn could tell you all about amortensia. Okay. So that's what you should be able to do by the end of the lesson. Now let's go through and take a look at it step by step. How do you do this stuff? What is a molecule to do when placed in water? So you have 4 choices for major entities present. In other words, what does most of it or greater than 50% of it look like? Choice number 1, do nothing. If it starts out a solid, it stays a solid. Or if it starts as a gas, it stays as a gas. So it does not change. And that's going to work well. We'll go through the groups. Option number 2 is to dissolve it. Dissolving means make it aqueous. So this one, solid goes to solid, gas goes to gas. This one, solid goes to aqueous. Dissociate, solid goes to ions. And ionize, this is for acids, and they also go to aqueous ions. Okay, so do nothing, dissolve it as aqueous, dissociate into its ions, ionize into its ions. Those are your 4 choices. All right, so these are the 7 different groups of compounds that you will be given. So you have to remember the rules for all 7. So which ones do nothing? They just keep their state. Elements, we already did the example of copper. Elements do nothing. And there's a second group here that does nothing. Actually, there's 3. What other ones from this group? So elements are gone. Take your pick. They do nothing. They just sit in whatever state they started. And it's these 2. Insoluble or nonpolar molecular compound. Insoluble, nonpolar molecular compound. So if they're molecules and they're nonpolar, they will not dissolve. They just keep their original state. Gasoline was an example of that. And then number 3 is low solubility ionics. So these are ionic compounds that don't dissolve in water, so they keep their state. In other words, they're always solids. Okay. Dissolve. So which of these dissolve? Those are gone. We have 4 left. Which ones dissolve? But they don't do anything else. And the answer would be soluble polar molecular compounds. Let's change our color up here. Let's go red. Soluble molecular compounds will dissolve. And the second one you probably don't know, and that's weak acids. Weak acids also dissolve, but they don't ionize. They ionize a little bit, but less than 50%. Okay, the last 2, and there's only 2 groups left, a strong acid and a highly soluble ionic compound. So which one dissociates? I hope you all get that one right. Highly soluble ionic compounds dissociate, and strong acids ionize greater than 50%. So that's the 7 rules that you must use your brain to remember. That's a light bulb and a brain. I know, amazing. So you got to think about these ones, okay? In chemistry, not only do you have to be good logic and good with math, you have to have a memory. You got to remember all these rules in order to classify any of those 7 compounds and do the correct thing. 7 groups, 4 choices as to what to do with any one of those 7. Okay, so this table is messy but important. So hopefully you've put that into your notes as well. Okay, so let's go through and practice a little bit here. Dissolving, the process in which a solute breaks into molecular or ionic particles surrounded by water. So why does dissolving work? What causes it? It's all about water being polar. So because water is polar, it will surround polar molecules and dissolve them, like this example of sucrose, where the positive poles of the water are surrounding the negative poles on the molecule and breaking it apart from the other solid sucrose molecules and getting it to dissolve. So it's really about attraction. The sucrose molecules are attracted to the water molecule, so they dissolve into it. And weak acids are also polar, so they also do the same thing. They will dissolve into the water, okay, because of the attraction, the polarity. Okay, dissociation is a little different. In dissociation, the water molecules are also polar, but this time they are breaking the ionic compound apart into its positive ion, positive cation, and negative anion. And you will notice in this diagram, if we zoom in, that this positive is surrounded by all the negative poles of the water molecules, and this negative ion is surrounded by all the positive poles of the water molecule. So that's how water is able to break apart a crystal or a solid ionic compound. That is not easy to break apart ionic crystals, but water is able to do that because of the attractiveness to the opposite poles. Okay, so dissolving, dissociation, and these are examples of highly soluble ionic compounds dissociating into their ions. And if we wanted to show this as soluble, it's going from a solid table sugar in your sugar pot at home, dropped into a glass of water, becomes aqueous. So this is what dissolving looks like if you write it out. And these two are what dissociation looks like if you write out. This is called a dissociation equation. Okay, hopefully you got that. All right, so now you get a chance to practice this. So in your notes, I've given you 5 of these, and if you didn't print off the notes, you can just write these out on a sheet of paper. So what you're going to do is practice the dissociation equations, and all 5 of these have high solubility. So I'll save you a bit of time. You don't need to go and look them up. Every one of them is in this upper box for high solubility. You just need to know the formulas. So sodium fluoride, NaF, starts out as a solid. When we put it into water, it breaks apart into its ions. Na plus and F minus, aqueous. I just wanted to go back and check on this dissociation equation. Yes, they started as solids as well. Okay, so if you want to pause the video and try B, C, D, and E on your own, and then come back and check to see how you did, and I'll fire them up in the meantime so that they're ready to go when you come back to the video. Okay, sodium phosphate, 3 Na pluses, aqueous, and 1 PO4, 3 minus, aqueous. Cobalt 2 chloride, COCl2, dropped into water, becomes cobalt 2 plus, aqueous, and 2Cl minus, aqueous. So we're balancing these as well. Sometimes people will put H2O above the arrow to show that you're adding it into water. Okay, aluminum sulfate, Al, sulfate, SO4, 2 minus. 2 minus. So that's 2 of those, 3 of those. gives 2 Al3 pluses and 3 SO4 2 minus. Okay, on a slightly random note, I don't think my light in here is very good, but maybe you can see my tan on my face. I was outside all weekend doing yard work. Oh my gosh, my back is so sore. I'm so tired, but it was sure lovely to get out in the sun and dig up some soil and do a flower bed and do some weeding and blah, blah, blah. Just get out and be active a little bit. I'm lucky that I have a yard. If you have a yard, maybe you can go and do some yard work for your parents too. Pick up all the dog poop, rake the leaves, fertilize the lawn, start watering, all that stuff. Okay, last one, ammonium hydrogen phosphate. Ammonium, NH4, hydrogen phosphate, HPO4. That's a 2 minus. So that is 2 of those. That's a tricky one. You have to look up both of those polyatomic ions to get the correct formula. So that one dissociates into 2 NH4 pluses and 1 HPO4 2 minus aqueous. Okay, so hopefully those are reasonable for you guys for dissociation equations. That's a really important skill. And this is only for high solubility ionic compounds. Okay, low solubility, they stay together as a solid. Okay, hey, we're rolling along here. So solubility chart, I've already used it a little bit. It's on the back of your data sheet, so you'll need your solubility chart when you're doing these on your own. Remember to always look up the negative ions first and then go and search. So if I gave you calcium fluoride, you would look up the fluoride first, and then you go searching. Most things are very soluble, but calcium fluoride is not. So it's in the slightly soluble. And if I gave you copper iodide, same thing. Here's iodide. Most things are high, but copper 1 plus is low. Copper 2 plus is up there as high. Interesting. So copper 1 plus would stay together as a solid. And if it was made up of copper 2 plus, it would dissociate into its aqueous ions. How about that? Okay, moving on. Keeping the pace up because we've got a fair amount to cover here. Okay, we've talked about ionization already. So this happens with acids. Okay, and so here's hydrogen chloride, which is actually a gas, but when you add it to water, when you bubble it through water, it ionizes. So ionization, a lot of students confuse it with dissociation, but they are different. Okay, dissociation is separation of ions that already exist. In other words, it's an ionic compound. Ionization produces new ions that were not there, and it's from a molecular compound. Molecular compounds don't have ions in them. They're molecules. But acids are a special group of molecular compounds that, in the presence of water, can form 2 ions that were not previously there. So we always say that acids are a special group of molecular compounds that ionize. They're the only things that do it. And the rule is, if you are a strong acid, you are greater than 50% ionized. And if you are a weak acid, you are less than 50% ionized. So instead, you just become aqueous, whereas on the strong, you become H plus and something, let's fix that up, something minus, whatever the negative part of the acid is. Cl minus, F minus, and those are both aqueous as well. So strong acids versus weak. Okay, how are you going to know strong versus weak? Well, in your, hang on here. Is it not in here? Yes, here it is. Jumping ahead. On the back of your periodic table, there is a chart that gives you 3 of the 6 strong acids. Did you know there are only 6 strong acids? Everything else is weak. So the strong ones have a star beside them. Hydrochloric, nitric, sulfuric, And there's 3 more to add. By the way, bindimum secretion, bindimin, is also a strong acid, but it's magical, so we don't need to worry about it unless you're at Hogwarts. Okay. Please add these other 3 to your periodic table. We use them in Chem 30 as well, and you're allowed to have them on your periodic table. So they are hydrochloric, hydroiodic, so hydrogen chloride, hydrogen iodide, and hydrobromic. And then the last one is perchloric. Whoops. It's PERCHLORIC. So hydroiodic acid, hydrobromic acid, and perchloric acid. And their formulas are HI, HBr, and HClO4. They're all aqueous. So there are 6 strong acids that ionize. So star equals strong acid, ionize, IONIZE, greater than 50%. All the other acids are weak and they are aqueous, but less than 50%. So major entity present is they stay together as a molecule. Oh, how are you guys doing? I told you lots of stuff today. Oh my gosh. Okay. We're going to skip this chart for today and we'll cover it tomorrow instead. Okay. Because we got a lot of stuff to get through. So those of you taking Spanish, I don't know where the little accent goes. Maybe there. Mañana. Tomorrow. Okay. Maybe it's a squiggly over the end. I have no idea. Okay. So we'll do that one tomorrow. Okay. Coming back. All right. So ionic compounds, easy. Use a solubility chart to figure them out. But if they are molecular compounds, not so easy. You have to know whether or not they are polar. Now you can take time to draw them out and do the electronegativities and figure out if they're polar, but let's save some time. Hydrocarbons are all nonpolar. So anything made up of just hydrogen and carbon is nonpolar, which means it does not dissolve in water. It has low solubility. Any of the oil and wax products, so candle wax, C25, H52, gasoline for your car, propane in your barbecue, methane to heat your house, none of these things dissolve in water. They're all nonpolar. These guys are all polar, and with the exception of ammonia, the rest of them all have OH groups in them, and that's why they're very polar. So for example, hydrogen peroxide has 2 OH groups. It is very polar. These are all highly soluble in water, or they all dissolve as aqueous. Polar equals aqueous. They dissolve in water. So look at formulas that have hydrogens and oxygens. Sometimes you'll see the OH in the formula. Sometimes it's not there. It's not written, but it's there because this thing has 12 hydrogens and 6 oxygens. So I can guarantee you glucose and sucrose both have some OH groups made up of those hydrogen and oxygen atoms, which makes them polar. And we all know that sugars dissolve in water, and so do alcohols dissolve in water. Okay, so you can remember those general rules rather than trying to memorize everything in the chart. Hydrocarbons with oxygen in them are high solubility, and hydrocarbons that are just hydrogen and carbon are nonpolar, low solubility. Oh my gosh, lots of stuff to remember. Okay, hope you're doing okay. We're going through this fast, and I think we're actually getting close to being done. Okay, so this chart is a summary from your textbook. So I didn't put it in your notes just because it's examples of all the things that we just did. If you're an ionic compound and you have high solubility, you dissociate. If you have low solubility, you stay together as a solid. Bases are also ionic compounds, so they follow the same rules. High solubility, they dissociate into their ions. Low solubility, they stay as a solid. So bases are ionic compounds that just happen to have a basic property. They turn litmus paper blue. Now, molecular substances, if they are high solubility, they're polar and they dissolve. And if they are low solubility, they are non-polar and they do not dissolve. They keep their state, gas, liquid, or solid, whatever they were when they went into the water. Strong acids, high, they ionize. Can I fit that in there? I'll write it over here. Because greater than 50% of them ionizes, we write the ions. For weak acids, they are highly soluble, so they do dissolve, aqueous, but less than 50% ionized, so we don't write the ions because we are doing the major entity, the most common thing present. And so most of this acid stays together as a molecule. Even though it has some ions, it's mostly a molecule. And elements are easy. None of them dissolve. They're all low. Copper is a solid, nitrogen is a gas. In water, it's a solid, and nitrogen is a gas. Phew. That was a lot of information. How are we doing? Are we just about through? Let's see. Okay, this chart summarizes the 4 things you need to do. It summarizes what we just talked about there. So we've covered all that information. Whoa. Okay. So that's good. And we're going to do this problem tomorrow as well. I don't know which symbols they are. So tomorrow for that one, which means we're done. Wow. So I think the best thing for you to do is where did I put it? In your notes, there's a worksheet. I think it's on the bottom of this lesson. Yes, it is right here. So these, I think I attached this. I can't remember what I did. I'll figure it out. I would like you to do all of these. And the nice thing about this worksheet is they're in order. So it gives you ionic compounds. So you know that for ionic compounds, you're going to dissociate them if they have high solubility, which these all do. These have low solubility, so they're going to stay as solids. These are unknown, so you have to figure it out. Are they high or low? And then go ahead and do what you need to do, either dissociate them or solid. And then you go on to the next group, moleculars. And then we've got elements and acids. And then at the end, we have an all mixed up section that has elements, acids, ionics, moleculars, high solubility, low solubility, strong acid, weak acid. So this is the challenging section after you've done everything else. That'll be enough for today to get you going on that. And this is on this slide only. I know it's not in the study guide. And then the answer to this, I will post it. I don't know where it is. I'll have to find it and post the answer key to this one on Google Classroom. Okay. All right. Thanks for hanging in there. I know it was a lot of information today. Doing this worksheet will really help to sort of solidify the ideas that you learned today. And hopefully you're doing the Harry Potter challenges as well. And I think, depending what time you see this at, I'm going to try a Kahoot tomorrow, well, today, Monday, as well. I got to figure that out to make sure it'll work. So I'll send you guys an email if I get the Kahoot up and running, if I'm able to figure out that technology, Harry Potter Kahoot. Okay, take care, everybody.